Hi, everybody. So now we're going to talk about in this video dimension, as it's all the results we learned about dimensions of spaces, Rn spaces, all that will carry over because of the coordinate theorem. So I won't be proving a whole lot very much. The first one is that if you ever have a basis of a vector space, they always have the same number of vectors. And that's because of a theorem we learned before, that if you have a basis, anything more of it can't be independent. Anything less than it can't span the space. So then if you have a basis, you have to have this fixed number. So that's nice. That means that if you ever have a vector space that has a finite number of vectors in its basis, it will always have the same number. So we can then associate what we call the dimension of a vector space. It's just the number of vectors in the basis, just like before. Now, from here, there are already known to be certain standard bases for certain spaces. For example, the set of polynomials of degree n or less actually has n plus 1 vectors in it. So the dimension of P sub n is n plus 1. The set of matrices of size m by n has m times n vectors in its standard basis. So then the dimension of that space is m times n. But you can have a vector space that's infinitely dimensional because, well, you'd have to have an infinite number of vectors to describe the span. A good example of that is just a set of polynomials. It has a basis that's infinite in size, so its dimension is considered infinite. Now, there's a bunch of theorems that we have that we can carry right over because of the coordinate theorem. None of these need to be proved. I'll just write them all and just use them. So if you ever have n linearly independent vectors in V that you know has a basis of n vectors, then those n linearly independent vectors is a basis. That means you don't have to prove it spans the space. Just showing it's independent is enough. That automatically shows that's a basis. If you ever have more than n vectors in this n-dimensional space, it's automatically linearly dependent. If you ever have n vectors in an n-dimensional vector space and those n vectors span the space, then they instantly are linearly independent and therefore are a basis. So you only need to show one. If you ever have n vectors, if you show it either is independent or it spans a space, it's automatically a basis. You don't have to do the other part of the proof. If you ever have less than n vectors in an n-dimensional space, then it can't span the space. Any spanning set can be reduced to be a basis of V. Remember, I showed you how to do that before. In Rn. There's a way, you just think of it as a bunch of vectors as spanning a space. That makes the span of a column, corresponds to a column space. And you can row reduce that to get a basis for that column space. That's reducing it. You can also have, if you ever have a set of vectors, a bunch of set of vectors that are linearly independent, you can then extend that set to become a basis for V. And I showed you how to do that too. I did that using the vector space W and W perp, and using the basis for W perp to go and extend the basis. There's another way to do it. I'm going to show you how to do it. It's computationally a little easier to do. It just wasn't as fun as doing W perp before. I use either technique, depends upon what I need at the time. So then you have these 6 statements. Now, the thing is, though, is that the proofs I gave you in order to do this process of extending or reducing to a basis relied upon a matrix. This doesn't work really well if the basis has an infinite number of vectors in it. So we have what's called the plus and minus theorem. This theorem is in the homework section. Some people don't even call it a name. They just refer to the process. And it goes like this, the plus version. If you have a bunch of vectors that are linearly independent, but yet don't span the space, so it's too small, there's another vector out there then that's not in the span of these vectors. Take that vector, throw it into the set of this finite set of vectors. The result will actually also still be linearly independent. The reason is that if they're dependent, then one vector has to be a linear combination of what came before it, and it would have to be the vector we just added. But that would mean that vectors in the span of those vectors, which is not true. Conversely, basically it's the same argument. If you have a bunch of vectors that are dependent, then you can take one vector out and it would still span the space. The vector you take out must be a linear combination of what came before it, or at least the other vectors. And again, the argument's basically the same. This is again called the plus minus theorem. It's a way to add vectors and not lose independence, or to subtract vectors and not use spanning, not lose spanning. I'll show you how to use it. So for example, I'm going to show you right now that these two vectors is a basis for P2. It's incredibly easy to do. Incredibly easy to do. I'll call these vectors for a minute. I'll call these vectors for a minute, U and V, when you do so. So the vector P, I'll call P. Vector P of X will be the vector 1 minus X, and the vector Q of X is going to be the vector 1 plus X. And I'll use the standard basis for P, 1. So then P, the standard vector for it, the coordinates for it would then be 1, -1. And the coordinates for Q relative to the standard basis would be the vector 1, 1. But since the set 1, -1 and 1, 1 is linearly independent in R2, that means then by the coordinate theorem that 1 minus X, 1 plus X is linearly independent in P2. Also, by the theorem I just gave you, the dimension of, P1. The dimension of P1 is 2. There's two vectors in a standard basis, 1 and X. So by the theorem I just gave you, 1 minus X, 1 plus X is a basis for P1, for P1. That's it. That's it. So now you know that those two vectors together form a basis for P1. Now to reduce, we're going to reduce a set that spans some space, and I want to go and find a basis for it. So there's a number of ways to do so. There are a number of ways to do so. One way is to go and look at the coordinates of these vectors. That would then be the span of some space in R4. You can think of that span as a column space, and all you want to do then is find a basis for that column space. That's one way to attack the problem. The other way is to use the plus minus theorem, which is if you can find a bunch of, if the vectors are not independent right now, then there must be one vector that's a linear combination that came before it. You then remove that vector. The result then has to be the same span, because by removing the vectors in the plus minus theorem, you don't change the span. So I'll quickly do both. So then the coordinates of these vectors relative to the standard basis E in M22 is the set. I'd have 1, 0, 0, 1. I'd have 0, 1, 1, 0. I'd have 1, -1, -1, 1. And you'd have 1, 0, 0, -1. So then I want to know then are these four vectors linearly independent, or are they not? They're not. They're not independent. One vector is obviously a linear combination of what came before them. So what I could do is I could consider the span of this space. The span of the space is something, I don't care. That's actually the same as saying it's the column space of the matrix 1, 0, 0, 1, 0, 1, 1, 0, 1, -1, -1, 1, and 1, 0, 0, negative 1. If I can find a basis for that column space, I can then find this. That's the same as the span of its columns, but the columns will be coordinate vectors, which would correspond to the original vectors. So then I can then take the matrix 1, 0, 0, 1, 0, 1, 1, 0, 1, negative 1, negative 1, 1, 1, 0, 0, negative 1, and you could row reduce it. When you row reduce it, it would become the matrix. You'd get a 1, 0, 0, 0. You get a 0, a 1, 0, 0. This one, though, you'd get a 0, a negative. No, you wouldn't get 0. You get 1. All right, you get 1. Yeah, you get 1. You get negative 1, 0, 0, and then 0, 0, 1, 0. And if you remember, the columns that correspond to the leading entries, those columns form a basis for the span. So because of that, the vectors 1, 0, 0, 1, 0, 1, 1, 0, and 1, 0, 0, negative 1, these are a basis for the column space of that matrix. But that means then that these coordinate vectors go back then to the vector space, and the corresponding vectors in V would have to be a basis for the span of the space that we were talking about. So then this vector, and that vector in V, those three vectors form a basis for the span of that space. So that's one way to do it. That's like beating it to death. That's like using the coordinate theorem for all its glory. Another way to do it is to notice that this vector here is a linear combination of what came before it. It winds up being 1 times this matrix minus 1 times this matrix. That's equal to this vector. So by the plus minus theorem, I can remove this vector and I don't change the span. But the last three vectors are obviously linearly independent. So if they still span the space and now the set of these three vectors is linearly independent, then of course, that means that these three vectors form a basis for the span of these four. And that's the exact same work as what I did before with the coordinate theorem. It's just faster because the coordinate theorem, that plus minus theorem, takes care of the coordinate theorem, all that work I'd have to do. Cool. So let's just do it again. I want to extend these two vectors to be a basis for P2, the set of polynomials of degree 2 or less. So there's a bunch of ways to do it. One way to do it is to go and, to go do it like I did before, like this. So then these vectors have coordinates, which is 1, negative 1, 0, 1, 1, 0, relative to the standard basis. E for P for P2. Okay, so then they obviously, though, the dimension of P2 is 3. So then these two vectors these coordinates do not span R3. And therefore, these two vectors are not a basis for P2. I mean, they're clearly independent, though. They're not multiple of each other. So they're clearly independent, though. So then I can then go and try to find a way to extend these two vectors in R2 to be a basis for R. Shoot. Let me try that again. I can take these two vectors in R3 and I can extend them to be a basis in R3. Once I can extend them to be a basis in R3, those will be then coordinate vectors. I can then pull it back to find the corresponding vectors in P2. So how to do that? Well, there's a couple ways to do it. One way is to go and look at the span of this set. That would then be a column space. I want to find a basis for the perpendicular component. That would then lead to a vector. That's one way to go about it. Another way is to do this sneaky trick, and that is, notice that if you take the vectors 1, -1, 0, 1, 1, 0, and then just slap on the normal standard basis for E1 for R3. That'd be E1, E2, E3. These things certainly span R3. These guys span R3. So then I can take these vectors in R3 and I can reduce it to be a basis in R3. We do that by using a matrix. So then I think of this as the span of these vectors is the same as the column space of a matrix. I'll find a basis for that column space. To find the basis of the column space, I take the matrix. Oh, 1, 1, 0, 0. And then I'd have 0, 1, 0. And then I have 0, 0, 1. And I row reduce it. When you row reduce it, you get 1, 0, 0, 0, 1, 0. You'd have what? What would you have then? I'm trying to do the arithmetic here in my head. So that would be be 1/2. Maybe 1/2. Maybe 1/2. Yeah, 1/2, 1/2, 0. This would then be this would be negative 1/2, negative 1/2, negative 1/2, and 0. And then you'd have 0, 0, 1. Again, if you just take the leading entries, and then find the corresponding columns, those columns are a basis for R3. So that means then that the set 1, -1, 0, 1, 1, 0, and 0, 0, 1, those things span R3. Well, now just think of them as coordinate vectors and bring it back. So therefore, the set 1 minus x, 1 plus x, and x squared, that's a basis then for P2. That's it. That's how it's done. That's one way if you want to use the coordinate theorem, just bash the problem to death. The other way, though, is to use the plus minus theorem. Notice that the two vectors, 1 plus x and 1 minus x, can't add to be anything that has an x squared in it. So x squared is clearly not in their span. So by the plus version, if I were to go and take this set, if I take this set of linearly independent vectors and I throw in the vector that's not in their span, that is still in P2, x squared, the resulting three vectors would have to still be linearly independent. So by the plus minus theorem, these vectors, 1 minus x, 1 plus x, and x squared, they have to be linearly independent. But then P2 is dimension 3. So now I have three vectors that are linearly independent in P2. They're all Maclaurin basis. That's a lot faster, isn't it? That's a lot, last idea is a lot faster. It's harder though to see because you have to see a vector that's not in the span. So doing so may be tedious. Okay, so then we're now down to our last basic idea about dimensions and trying to get an idea similar to what we did in R3, R4, R5. Notice that the plane is smaller in size than in R3. The plane is dimension 2 and R3 is dimension 3. So we can use this idea to generalize comparing spaces in a larger space. So suppose that you have a vector space V, finite dimensional, and you have a vector space W inside of it. In other words, you have a subspace. Well then, if V is finite dimensional, then W has to be finite dimensional, and the dimension of W has to be less than the dimension of V. The reason why it's really obvious. What if the dimension of W is more than the dimension of V? But that would then mean that there is a certain number of vectors in W that are linearly independent of W. But then those same vectors have to be linearly independent also in V because the operations don't change. But we can't have more than the dimension in V that are linearly independent. So therefore, the number of vectors that are linearly independent in W can't exceed the number of vectors in the dimension of V. And that means the dimension of W is less than or equal to the dimension of V. For the exact same reason, just arguing with spanning this time, that you get that the two things are exactly the same if their dimensions are the same. So if the dimensions are the same, the spaces are the same. If the spaces are the same, of course, their dimensions are the same. That's a nice little easy result. It's basically giving you a generalization of what you know when you have a plane inside of R3. The dimension of the plane is only 2, and the dimension of R3 is 3. So this subspace is smaller in dimension than the overall vector space. It just can't exceed it. And I believe that's enough for that theorem.